So welcome to Math 150. What we're going to do today is we're going to continue with integration. We're going to talk about applications of multivariable integration. We're going to try to figure out what is the volume of the sphere in n-dimensional space. Now, everybody should remember polar coordinates without any trouble. Spherical coordinates you should remember with a little bit of trouble. You might have to draw the picture. And of course, the physicists and the mathematicians have slightly different pronunciations of how they choose their axes and how they choose what variable is where. If you want to go further, you actually need spherical coordinates in higher dimensional spaces, 4, 5, 6. At that point, we give up trying to draw. My artwork is bad enough in 2 and 3 dimensional space. I'm not going to try to draw something in 17 dimensional space. But you can still write down what's going on. So if we had 17 dimensional space, how many angles do you think we have in 17 dimensional space? What would you guess? So go back to in 16. In 2-dimensional space, we had 1 angle. In 3-dimensional space, we had 2 angles. So we should probably have 16 angles and a radius. And then you have to figure out which angles go from 0 to pi, which angles go from 0 to 2 pi, what are the correspondence, x1 equals what, x3 equals what, oh Lord. We're going to see a way to actually deal with a lot of problems in n-dimensional spherical coordinates without actually writing them down. And again, part of what I'm doing is I want you to see applications. I also want a chance to review a lot of the concepts we've been doing. So we talked last time about the gamma function. And so the gamma function, which we saw when we did the baseball lecture, is defined as gamma of s is the integral from 0 to infinity, e to the negative x, x to the s minus 1 dx. And this converges if the real part of s is greater than 0. I'm just writing real part because I will be teaching complex analysis next year, and in that we actually can consider this integral when s is a complex number. For us, we just really want s to be a real number. So we showed gamma of n plus 1 is n gamma of n if n greater than equal to 1 is a positive integer. We actually didn't need it to be a positive integer. We just actually needed n to be, I'll do this way, greater than 0. So what was great about this is this allowed us to get some values by knowing other values. So for example, we showed directly gamma 1 equals 1, gamma 2 equals 1. So gamma of 3 would be gamma of 2 plus 1. And so this would just be taking n equals 2. It would be 2 times gamma of 2. I'm sorry, 2 times, of gamma of 2, which is 2 times 1 is 1 factorial. Gamma of 4 would be gamma of 3 plus 1. So this would just be taking n equals 3. It would be 3 times gamma of 3. It would be 3 times 2 factorial or 3 factorial. So gamma of n plus 1 is n factorial if n greater than or equal to 0 is an integer. So this is a really nice application. There's one other value of gamma that's worth knowing. So recall the Gaussian integral. So we showed that the integral from negative infinity to infinity, 1 over square root of 2 pi e to the negative x squared over 2 dx equals 1. So this was a probability density. So this is one of the key concepts. This really plays a huge role in later math classes. We saw probability densities when we did the baseball lecture. I want to calculate the probability of an event. Well, the probability of an event would be the area under the curve from A to B. This is one of the big applications of calculus. This is why you're taking 3 classes in the subject. We want to calculate probabilities of events. We showed that the way you integrate this is that you square the integral, you have x and y, you shift to polar, and then you take the square root. It's an amazing trick. We do not have a nice antiderivative for this. And there's another really big theme in calculus that's lurking in the background. that there's a lot of problems where I can't find an antiderivative, but I can actually find a nice value if I integrate from, say, minus infinity to infinity or 0 to infinity. That if you integrate over very nice ranges, we often have a nice value for the answer, but we do not have an antiderivative. So I can't give you a nice antiderivative. We talked about a Taylor series expansion for the antiderivative. We called it basically the error function. We said, well, we know the integral from negative infinity to 0 is 1/2, so we could play some games and get some Taylor series. And this is a chance to quickly review Taylor series from early in the semester and how we wrote things and expanded things like that. All right, does this look like the gamma function? And I'll use a different letter for the gamma function. I'll use as a variable 0 to infinity e to the minus u, u to the s minus 1 du. Does the Gaussian integral look like the gamma function? Does any of it look like it? And if so, which parts? Yeah, they both have an e to the negative something. So what might you take u to equal? So change variables. Let's let u equal negative x squared over 2. So du is going to be, when we take the derivative, the 2 is going to cancel the 2 in the denominator. And so we'll get negative x dx. Okay, well, we don't want x dx, we want dx. So we have to somehow convert the x to a u. So we get dx is negative x to the minus 1 du. But what is x? X is going to be, actually, we don't want the negative sign. We don't want the negative sign in the changing. Okay, so we want u to be x squared over 2. Du is going to be just x dx. So how would we solve for x? If u equals x squared over 2, what does x equal? No, I want to solve for x. So if u is x squared over 2, what does x equal as a function of u? Square root of almost of 2u. So it's just going to be 2u to the 1/2 du. So we now can replace dx with 2u to the 1/2 du. As x goes from minus infinity to infinity, what does u go from? So what will u go from? So u is x squared over 2. If x goes from minus infinity to infinity, what does u go from? Nope. Infinity to infinity. Right? U is x squared over 2. When you take negative infinity, this is a problem. So again, this is a point that's often not emphasized when you do u substitution. You have to make sure that your transformation is 1-to-1. If I give you one value of x, there's a unique value of u. If I give you one value of u, there's a unique value of x. Right now, 2 different values of x go to the same value of u. There's a problem with this. So what we can do is we can fix things. Instead of integrating from minus infinity to infinity, what we can do is the following. Let's change this and let's integrate from 0 and double it. Because the integrand is symmetric. If you integrate an even function from minus infinity to infinity, that's the same as integrating from 0 to infinity and doubling. If you integrate an odd function, a function where say f of 5 is the negative of f of negative 5, then it's going to cancel. So since my function is even, I can integrate from 0 to infinity and just double. Now, x doesn't go from negative infinity to infinity. X now goes from 0 to infinity, and u now goes from 0 to infinity. So when I do it like that, now everything is going to work nicely. And so now I get 2 integral u goes from 0 to infinity. 1 over square root of 2 pi doesn't change. E to the negative x squared over 2 just becomes e to the negative u. And then dx becomes 2u. Oh, and this was x to the minus 1, so this should be negative 1/2. So 2u to the minus 1/2 du. So the function, when we're integrating from minus infinity to infinity, we're integrating an even function. The value at 5 is the same as the value at negative 5. The value at 12 is the same as the value at negative 12. So if I just integrate from 0 to infinity and double it, that's the same as integrating from minus infinity to infinity. And we need to do that because if we want to do this change of variable, we saw the issue we had. We'd be integrating from infinity to infinity. That's integrating over a point that would just be a 0 integral. And so again, yes. So it's an even function if it only depends on even powers of x. So if you think about the Taylor series for cosine, it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. It only depends on even powers of x. So if you replace x with negative x, it doesn't change. Sine is an odd function. It only depends on odd powers of x. When you replace x with negative x, x goes to negative x. X cubed goes to negative the cube of x. X to the 5th goes to negative the 5th power of x. And so if I would integrate an odd function from minus infinity to infinity, I would expect to get 0. So for this function, it's looking a lot better now. So let's pull some things out. I've got a 2 to the negative 1/2. I have a 2 outside. I also have a square root of 2 down below, right? So if you look at it, all the 2's are going to cancel. I'm going to be left with 1 over the square root of pi. So I'll write it as maybe pi to the minus 1/2. Integral u goes from 0 to infinity, e to the negative u. And then I have u to the negative 1/2. Does that look very close to the gamma function? I don't care about the pi to the minus 1/2 outside. I've got an e to the minus u, which is great. I have a u to the negative 1/2. I want to have a u to the s minus 1. What would s equal? S would be a 1/2. So I could write this, if I wanted to, as 1/2 minus 1. That's the same as u to the negative 1/2. So this is going to just equal gamma of 1/2 times pi to the minus 1/2, and that equals 1. So gamma of 1/2 is going to be pi to the 1/2 or the square root of pi. This is one of the most important values of the gamma function. It's extremely important in statistics. How many of you are taking a statistics class or have taken one? When you see the standard normal, when you see the moments and all that stuff of the normal, it's coming from the gamma function. You could interpret things in a very interesting way. Gamma of n plus 1 is n factorial. Can somebody tell me the combinatorial meaning of n factorial? What does n factorial mean? That's what it means algebraically. It's n times n minus 1 times n minus 2. But combinatorial, can somebody tell me what does n factorial represent? So what would 3 factorial represent? I'm sorry? Well, so the number is 6. Well, it's the number of possible ways to arrange 3 people when order matters. We have 3 people sitting against the blackboard over there. We're not going to count you. You're too far away. Sorry. If you want to move your desk, we'll incorporate you. All right. So how many ways can I order the 3 of them when order matters? There's 6. I have 3 choices for who's closest to the door and most likely to either survive if there's a fire or open the door so that the rest of us can survive. Then once we choose who's first, we have 2 people left. There's 2 choices for who comes in second. And then there would be 1 choice remaining for who's third. So there's 6 or 3 factorial ways to order 3 people when order matters. This gamma function is a way to generalize the factorial function to non-integers. And this, strange result is gamma of -1/2 is really -1/2 factorial. The number of ways to order -1/2 of a person when order matters is the square root of pi. It's a strange number. What this means is just because something has an interpretation in one part does not mean that interpretation continues. When I'm putting in a positive integer, gamma of n plus 1 is n factorial. It's the number of ways to order n objects. This is not the number of ways to order -1/2 of a person. That doesn't make any sense. So always be careful about pushing something beyond the range where it makes sense. Yes?
Would we be asked to reproduce this on a test?
This would be an absolutely fair integral for you to do on a test. Yes, this is a Calc 1 integral. And this is why I'm trying to review stuff like this. This is a chance for me to review use substitution. This is a chance for me to review. You've got to be careful when you're doing use substitution that something was clearly wrong because we had the bounds going from infinity to infinity, which would just give us an integral of 0. But this is not that bad of an integral. The key part is realizing that we can do some kind of change of variable. In general, if I get to this is a very hard integral to do. We just happen to do the polar trick. I'm not going to give you anything as hard as needing to do the polar trick, but you should know that this integral is 1. This is an extremely important integral. All right, so now let's consider the following. So let's consider f of x1 through xn is going to be the product, k goes from 1 to n, 1 over square root of 2 pi e to the negative xk squared over 2. So product is very similar to a sum. In the sum, you add all the terms. Here we multiply all of them. So this is going to just be the same as 2 pi to the negative n halves e to the negative x1 squared plus ... plus xn squared over 2. So that's the function I want to integrate. And I want to integrate this function over all of space. So I want to integrate x1 goes from -infinity to infinity, ... xn goes from -infinity to infinity, 2 pi to the negative n halves e to the negative x1 squared plus xn squared over 2 dxn dx1. Yes?
What's that subscript you put in the first formula for x? Is that
That's a k. I'm doing a product over k. And so let me try to write it more cleanly. This integral just factors. This is just going to be the integral x1 goes from -infinity to infinity, 1 over square root of 2 pi e to the negative x1 squared over 2 dx1 ... integral xn goes from -infinity to infinity, 1 over square root of 2 pi e to the negative xn squared over 2 dxn. Again, this is now a way to review integrating over a box. This is why we like integrating over a box. My function f splits. So I don't have any cross terms. I don't have anything depending on x1 times x2. Because of this, I can break this n-dimensional integral up into n one-dimensional integrals. If I gave you something like e to the negative x1 squared times x2 squared times x3 squared, if I multiplied them all together, this would be a disaster. What does the first integral equal? So what would the first integral equal? So we're integrating from negative infinity to infinity, 1 over square root of 2 pi, e to the negative x1 squared over 2 dx1. What does that integral equal? 1. This is just the Gaussian integral. It's each one of them is equal to 1. So the final answer is 1. So if I just integrate this function, I just get 1. So I know some of you are considering, continuing in mathematics and stats. Some of you are considering taking, linear algebra. As you go further in mathematics, you will see more and more proofs. And so I want to start to do, towards the end of the semester, I want to start doing a few more challenging computations. I'm not going to have you do anything at this level on an exam, but I want you to be at least aware of stuff like this. We want to evaluate this integral. So the way a lot of advanced mathematics works is you try to evaluate something 2 different ways. We want to change coordinates. Anybody have any thoughts as to what would be the natural coordinates to change for this? It's not anything we've seen, but it's related to something we've seen. So what have you seen that looks similar to this? There are 2 things you've seen that look similar. What are your thoughts? So the integrand only depends on x1 squared plus dot 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 plus xn squared. It only depends on how far you are from the origin. Okay, so this is the key observation. So only depends on distance from origin. So since it only depends on the distance from the origin, what does this remind you of? Which coordinate changes did we have that were very nice for problems like this? Polar, what else? There's something higher dimensional than polar. Polar is the 2-dimensional version. Spherical is the 3-dimensional version. So this should be n-dimensional spherical coordinates. We need to figure out what n-dimensional spherical coordinates are. So this is going to be n-dimensional spherical coordinates. So a lot of this now is to get us ready for the last section of the course, where we're going to talk about the Jacobian and the change variable formula. We are not going to prove this in great detail. It's a lot easier once you know linear algebra. I want you to be aware of a formula like this. And so what we need to do is to figure out how x1 through xn converts to, let's say, rho, and then we need a bunch of angles. I'll call them theta 1, theta 2, and how many angles do I need? And -1. And then I need dx1, dxn is going to convert to some function, I'll call it g, depending on all of this stuff. D rho, d theta 1, d theta, and -1. We did a lecture, I think, early in the semester on the Pythagorean formula. And we talked about how you could do a dimensional analysis and sniff out a lot of the functional form. Let's see if we can sniff some of this out right now. I want to figure out how the volume elements change. If I doubled the radius, what do you think should happen? I need to have something of the form meters to the nth power. When you look at d rho through all the d thetas, what's the dimension of that? So what's the units of d rho? So what would be the units of d rho? You know, x1 through xn are all in meters. What's the units for the radius? Meters. Okay, so rho is in meters, but we've talked before. D theta is not in meters. What do I have to do to make d theta into meters? I multiply by rho. You know, the angle, if I want to go from the angle to the arc, I multiply. So what should I multiply? What power of rho do I need to multiply by? I'm sorry? Well, what power of rho? I need to get this to meters to the n. I've got a meters from the d rho, and that's it. N minus 1. Each angle needs a rho. So this would be rho to the n minus 1. And then I need some new function. Let's call it h of theta 1 through theta n minus 1 d rho, oops, d rho d theta 1 d theta n minus 1. I don't know exactly what that function h is. If you think back to what we did in polar, we had, you know, dx dy became r dr d theta. H was just identically 1 in polar. In spherical, it was sine of phi. I don't know what it is in n-dimensional spherical. Okay. So let's try to continue doing the integral. Good, it's still saving it. So this would equal I would have the integral of rho goes from 0 to infinity, 2 pi to the negative n halves, e to the negative rho squared over 2, rho to the n minus 1. And then I would have the integral of the theta 1 through theta n minus 1 over their ranges, h theta 1 theta n minus 1 d theta 1 d theta n minus 1. Okay. Everybody comfortable with what we have? We know what this integral equals. What does this integral equal? We just showed it equals 1. Does anybody recognize what we have over here? Does this look like anything you've seen before? Looks like the what? It's close to the Gaussian. I would use a different thing beginning with G than Gaussian. It's something that's related to the Gaussian at a special value. It's related to the gamma. So I'm not going to go through all the detail, but show this is gamma of something depending on n. You know, I'm going to resist the temptation to go too deeply into the pure math theory. I'm going to try to do enough to show you what's going on, so if you want to finish the calculation, you can. As a really good exercise, figure out what this is. You need to do a change of variables. What should your change of variables be? You know, try u equals what? what should you take? If you think this is a gamma function, what should we take u to equal? Not negative. We thought it's actually bad to put in the negative because then you have bad squares. Just do rho squared over 2. So it's a really nice exercise, to practice your change of variables. Take u to be rho squared over 2, and at the end of the day, this is going to be a nice gamma function. Do you think it's going to be easier to integrate if n is even or if n is odd? So if n is even, we're going to have rho to an odd power, and it's actually going to come out very nicely. So for instance, if I take n equals 2, then I get a rho. Oh, good, rho squared rho, beautiful. It's going to work out very nicely. If I take rho to be 4, then I'll have a rho cubed. If I integrate by parts twice, it's going to come out nice. So it turns out that if n is even, you're going to get gamma of an integer. It turns out if n is odd, you're going to get gamma of 1/2 when you do things all the way down. That's why I had to do gamma of 1/2 so that we know what it is. So we know this whole thing is 1. This part is just a gamma function. If n is an even number, it turns out to be something we can evaluate very easily. If n is an odd number, we have to do a little bit more work, but we can actually evaluate it, and we'll get something involving square roots of pi. We're now left with just what is this piece over here? And this is basically going to be the surface area of the n-dimensional sphere. And so from a formula like this, I can get a formula for the surface area. And once I know the surface area, I can get the volume. For spheres, there's a really nice relationship between volume and surface area. We saw some of this in lower dimensions. So when n equals 1, we have, we have a circle. We have the perimeter is 2 pi r, and the area is pi r squared. What's the relationship between them? How do we get from area to perimeter? How do we get from perimeter to area? Well, let's write down, sorry, this is n equals 2. Let's do one more. N equals 3, we have a sphere. The area is 4 pi r squared, and the volume is 4/3 pi r cubed. How do we get from one to the other?
Or the
Other way around. Other way around. The integral of the surface area is the volume, or the derivative of the volume is the surface area. If you imagine what's going on, here's the area with a radius of r, and then I'm going to extend it, to delta r. And if I look at area of r plus delta r minus the area of r over delta r, this is going to be approximately equal to the perimeter at r times delta r. If I want to just try to calculate, what is the area of that small little sliver between them? Its thickness is basically delta r. So if I cut things out, it seems like it should be like perimeter times delta r. So if I take the limit, the derivative of the area should be the perimeter. You have to make this a little bit more rigorous, but this is a nice way to remember the different formulas. And so you can do the same thing with the sphere in higher dimensions. If I know the surface area, if I bump it up a little bit, I'm getting the volume. So take a sphere of radius r, take a sphere of radius r plus delta r. What's the volume of that shell in between them? It's going to just be essentially the surface area times delta r. And so if we divide this by delta r, and then we take the limit as delta r goes to 0, we get the derivative of the area is the perimeter. And so why is this useful? Well, in terms of what's going on here, the only thing I don't know is the surface area. With a little bit of work, you can interpret what we're doing here as this is going to give us the surface area. Because when I'm thinking about my integration, my function is constant on the surface of the n-dimensional sphere. It only depends on my distance from the origin. So on any shell of the same distance, I'm going to get the same value. And so because of this, I can interpret this with a little bit of work as this is the surface area of the n-dimensional unit sphere. And then the rho is just going to change which one I'm at. Once I know the surface area of the n sphere, by just integrating that, I can get the volume. And so this allows us to calculate the n-dimensional volume. We can even figure out how things change, what fraction of the hypercube is actually covered by the sphere as you get bigger and bigger and bigger. So this is a really nice application of what we're doing. It's a great way of reviewing a lot of things that go on. And it also emphasizes a really key point. For a lot of problems that you're doing, focus on what matters. For Lagrange multipliers, do I care about all the variables equally? No. Yeah. These are not my children. I can easily say, I don't care about lambda. I'm not going to get in trouble. No one's going to call anybody on me and say, my professor doesn't care about lambda. I don't. Why do we use lambda? So why do we look at lambda? So when we do Lagrange multipliers, if we don't care about lambda at the end of the day, it's not quite a placeholder for convergence. Close. It helps us with the calculation. And so a lot of times, we might take ratios of both sides and cancel the lambdas. It gives us, an extra, variable. It gives us things to help with. But at the end of the day, we're trying to find candidate points. I don't care about the value of lambda at the end of the day. It's just I needed to have enough, unknowns. You've got to be, of course, very careful. If you want to take ratios and do Lagrange multipliers and try to solve for things, you always have to break into cases. What if something is 0? So always when you're doing Lagrange multipliers, if I have 0, I'm going to handle that case separately, and then I'm going to look at everything else. So over here, what's really important is, do we have to write down what h is? Do we have to write down what the coordinates are? No. To calculate the volume of the n-dimensional sphere, we actually don't need to write down the n-dimensional spherical coordinates. This is somewhat similar to Lagrange multipliers. This is a real key idea and technique in mathematics. I just need to know that there's something, and I can put this in as a placeholder, and I can do my calculations. I don't actually need to know the functional form. If you want for extra credit, don't look it up, but try to figure out what would be the answer in 4-dimensional space. What would be the answer in n-dimensional space? Try to figure out what would the change of variables be. How would you convert from Cartesian to n-dimensional spherical? And just see how bad it is. Try to figure out what the ranges would be. But this is a key idea, which we've seen before. For a lot of calculations, I don't actually need to know the details. I just need to know that there's something there. We saw that when we did the proof of the fundamental theorem of calculus. We kept using what theorem? The mean value theorem, right? This is the friends, the mean value theorem. And it just says there is some point such that this happens. We don't need to know where that point is. We just need to know that there is such a point, and then we can do the calculation. And so this allows us to calculate one of the most important objects in mathematics, the volume of the n-dimensional sphere. And this is used in a lot of normalization problems. Okay, so you're continuing. Let's say I give you the following: x over a squared plus y over b squared equals 1. What kind of shape is this? It's an ellipse. And so there are rules, depending on which book in terms of what goes on. They often assume a is greater than b. And so some people say a always goes underneath x. Other people say a is always the larger one. And then there's relationships between the various things. So you have to just be a little bit careful sometimes as to what source are you using. Let's say I want to calculate the area of the ellipse. So can somebody give me an equation that would allow me to calculate the area of the ellipse? So do you think it's going to give me at least a word that I should be using to calculate the area? I should be finding. So what technique would I use to find an area? The integral. Okay, one-dimensional integral, two-dimensional integral. What do you want to do? Two-dimensional. All right. So let's just find maybe the area of 1/4 and multiply by 4. So the area is going to be 4 times the integral. Do you want to fix x or do you want to fix y? Which do you want to fix first? Okay, so we're going to fix y. So if we fix y, for a fixed value of y is going to go from from 0 to b, and then x is going to go from 0 to the square root of 1 minus y over b squared. And if I'm finding the integral, the double integral that's going to give me the area, what should my integrand be? What function do I integrate if I want to get the area? I'm sorry? I want to find the area. So what function should I integrate over the region to get the area? I'm sorry? Why would that give me the area? It's a very simple function. Just one, right? If I want to find the area, if I integrate the function 1 over the whole region, it's just going to give me the area. So we just integrate the function 1 dx dy. So let's change variables. Let's let u equal x over a, and let's let v equal y over b. So au equals x, bv equals y, dx is going to be a du, dy is going to be b dv, dx dy is going to be ab du dv. Yes? Just basically above each point, you go up 1 unit. And so if you think about that, it would give you a 3-dimensional object. And the area of the 3-dimensional object would be the area of the base times the height, because the height is constant. So if I want to get the area of any quantity, I just integrate the function 1. And then it will just give me the area. I want to. So you'll see why in a moment this is a good change of variables. So if you look at it, x over a squared plus y over b squared equals 1. What does this become in UV space? What's x over a? What does that become in UV space? U. So I get u squared plus v squared equals 1. This is a circle. So if I change from xy space to UV space, my region becomes a circle. Let's look at what the integrand becomes. 4 is still going to be a 4. Now, as y goes from 0 to b, what is the range of v going to be? V is going to go from 0 to what? So y equals b times v. So what's the range of v going to be? Well, y equals b times b, right? Y goes from 0 to b. When y equals 0, b equals 0. What does v equal when y equals b? Just equals 1. Now let's look at what's the range going to be for x. When x equals, I'm sorry, not x, u. When x equals 0, what's u going to equal? 0. And now, when we take the square root of 1 minus y over b squared, well, y over b is just, so this is the square root of 1 minus v squared, 1. And what does dx dy become? It becomes just ab. And then I'll get du dv. So this is just going to be 4ab times the integral v goes from 0 to 1, integral u goes from 0 to the square root of 1 minus v squared, 1 du dv. Can anybody tell me what that double integral is? Not 0, integrating the function 1, so it should be something positive. What's my region? Geometrically, what's my region? A circle. I'm integrating, basically over a circle. V goes from 0 to 1, u goes from 0 to the square root of 1 minus v squared. How much of a circle am I integrating over? A quarter. What's the radius of the circle? 1. So I have 1/4 the area of a circle of radius 1. Oh, oops, there's no pi over here. So the 4's cancel, and I get pi ab. So we actually just found, yes, from the bounds of integration. So if you look at what we're integrating, we have u squared plus v squared equals 1. We have v goes from 0 to 1, and we have u goes from 0 to the square root of 1 minus v squared. So if I fix a value of v, here's v, here's u, and I see just how far do I go, this gives me a quarter circle. So I recognize geometrically that what I have is just a quarter circle. So this is an example of the change of variable formula. This is a very special case, a very simple case where I'm just rescaling x, I'm rescaling y. So rather than measuring things in meters, I'm measuring things in feet. And this allows us to say, well, look, yes, it looks like an ellipse, but if I change my coordinates, it now looks like a circle. Oh, I know how to do a circle. The general change of variable formula, which we're only going to briefly touch on, is handling more general situations like this. Is how do you take nasty regions and change them? But at the end of the day today, we actually got the formula for the area of a circle. This matches what we did with the Monte Carlo numerical integration. So everything is consistent. All right, so this is a good place to stop.